So how do computers learn? And how do they mimic the learning process that humans and other higher order animals use? Well, we have to step back for a moment because what is learning? Define learning. Well, I might define learning as getting better at doing something. But what does doing something mean, and how do you define getting better at it? Well, doing something would be performing a task. There are physical tasks like playing the piano, running really fast, putting together a model airplane. Then there are mental tasks like playing chess, doing your math homework, or deciding whether somebody is bluffing when they're betting on a hand of poker. And then tasks that we take for granted, at least most of us do, that we really don't think of as learning tasks, but they are, such as walking. Now you'll notice, as I went through these, every single one of them, you intuitively have a sense of what getting better at it means. Getting better at playing the piano means you don't hit the wrong notes and you can play more complex music. Getting better at running means you can run faster and you pass out after the finish line instead of before it. Getting better at chess means you win, or at least you lose in a manner that's less embarrassing. The point I'm trying to make is that a task and getting better at that task, doing something and doing something better, is arbitrary. We define what that means. We do that for ourselves in the real world, and we do that for the computer when we are training something like a neural network. We define what the task is, and we define what it means to get better. And the algorithm has been developed by very smart people ever since the early 60s, and I think a bit before that, that allows you to massage the numbers in your computer program to get better according to your definition. So how do higher order animals like humans learn? It's something called reinforcement learning. Basically, we have a feedback system. Imagine that you want to throw a dart and hit a target on the wall. So you throw it, and you don't hit where you wanted to hit. So you try again and again and again and again. And you're receiving feedback as in where it's hitting. Right? That's your feedback. And you have a goal in mind. You know what it means to get better is perhaps getting closer to the bullseye. That's what you want. So what you do is experiment. You try holding your hand different. You try different speeds, different angles. You try over and over and over. You make minute adjustments, and you see what happened, and you absorb that, and you see what happened, and you absorb that. And eventually, with enough time, days if you're talented, months if you're not, or if you go take classes, that can help. But the point is, over time, you get better using this feedback, and eventually you'll hit the bullseye. And then the next time you throw it, you won't, but you had that feedback, and then if you keep practicing, you'll hit it more often, and you just successfully get better and better and better, and if you devoted your entire life to this, you could hit the bullseye every single time, no matter what you did. That is the training of an AI in the computer. We define the task, we define what it means to get better, and then we just iterate, using something called stochastic gradient descent is quite popular. I'll get into that in a future video. But we use math to inch it closer and closer. Every time we run the neural network and it's wrong, we know how wrong it is, and we change it so that it's just a little bit less wrong. And then next time, just a little bit less wrong. Exactly the same way. The history of artificial intelligence, neural networks, and all this stuff is fascinating. Basically, neurologists have been trying to figure out how the brain works. So they've studied the brain, they've studied neurons, and while they were doing this, we invented computers. We had math to think about the brain before this. They actually came up with the concept of an artificial neuron before there were computers, but that was of limited utility without computers, obviously. But the study of neurology and the study of computer science proceeded along, and at some point, the people who had the computers said, we can do some fancy things here. We're trying to make the computers smarter. We're trying to make them faster and do more things. Well, the brain is pretty good at doing things. Why don't we try doing things like the brain does? So they came up with a simplified version based on the original artificial neuron called a perceptron, and the first artificial neural network was born. And unsurprisingly, it was pretty good for its time. So the computer scientists were, trying to mimic the human brain and doing exciting things with that. But eventually, the computer scientists said, you know what? These are computers. They can do whatever we want. We don't have to try and exactly mimic the neuron. We can do some sillier things. So they started to experiment rather than just cleaving to what the neurologists had discovered, and they managed to make a few interesting things happen. And then the neurologists kind of peeked over their shoulders and said, what are you doing over there? And the neurologists saw what the computer scientists were doing, and they said, So they went back to their brains, their neurons, and started tinkering, started looking around at what monkeys were doing, started doing some experiments in learning, and said, well, would you look at that? They discovered that the monkeys were learning in a similar way to what the computer scientists had just kind of said, well, why don't we do this? And then the neurologists studied that, and then the computer scientists were peeking over the neurologist's shoulders and said, ooh, that's an even better way to do it. So then the computer scientists took that knowledge back over, and AI began to explode. Now, to be clear, artificial intelligence, AI, as in a computer life form, we haven't made one yet. No one has made one yet. And you might just call me pedantic, and I guess I am. AI is a common phrase to use to describe a computer program that seems pretty smart. But I would actually say AI is a life form, independent. It exists, it grows, it learns. We start having ethical questions. Right now, we don't have any computer programs that there are ethical questions about deleting. The moment you have a question and say, is it actually right for me to delete this program? That's when we've made an AI. But, like I said, that's pedantry, and we'll just call it AI because that's what everybody else does. Here's another fun fact. When you're doing AI, you don't have to use an artificial neural network. You always do, and there's reasons for that. The main reason being, it works really well here. There's a reason it works really well here. We're not doing it because it works here. It works here for the same reason it works in a computer. It's a really good model. But a neural network is just math. It's a glob of math. And you're using a neural network to approximate a function. I will explain all of this math and stuff in future videos. But basically, you can use any sort of interesting approximation method, multidimensional approximation method, just a bunch of math functions all slammed together to approximate the math of an AI. But we'll use neural networks because it's like, why would you use an abacus when you have a calculator kind of thing? We'll just do it the easy way. It works for a reason. But this is the learning method that both we and computers use. Think about a little baby. A little baby is born, and it doesn't know how to walk. Doesn't know how to do anything. It's flailing around. It can basically cry. Why can it cry, but it can't walk? Because crying is pretty simple. Open the mouth, breathe out, activate the glottis. But you're thinking, well, these are all things that we do when we're talking, yes. But think about a baby's cry. It's not perfect. It warbles. The baby sometimes doesn't even know how to keep its mouth open. Pay attention to a baby that was just born 8 seconds ago, and it's trying to cry. And it's crying, but it's crying kind of bad. It's not good at it yet. It even has to learn how to cry properly. And then walking and talking and all that is just more complex. But it's the same thing. Reinforcement learning. The baby does not understand how to make its arms work, but it understands just enough that, like there's a ball and it wants the ball. The baby understands ball, want ball. And so it's here and the ball is there and it's trying to reach for the ball. And instead of reaching for the ball, it goes like this. But the baby takes in that information. It sees, it feels, and knows that didn't work. So it tries again. And it keeps trying, and over time, it has figured out how to shakily, but somewhat, get the ball. And then it has to learn how to grip the ball, and then it gets smoother, and then it learns how to crawl over to the ball, because it has a goal in mind. It wants that ball. And iteratively, the baby tries and fails and tries and fails and tries and fails, but gets a little better every time. In physical therapy, somebody who's been comatose for 16 years and finally gets up, they can't walk anymore. Part of it is strength. Part of it is they have to redevelop the muscles. But part of it is the cliche of they forgot how to walk. This is true. They literally forget how to walk and have to go through this process the baby goes through. It's faster. They have a head start. But it's basically the same thing. After 16 years, even with mechanical assistance because they don't have the strength, they're flailing around. They can barely do anything. But then very rapidly, the reinforcement kicks in and their body readjusts and then they can start doing things again. It's just the same thing over and over and over and over and over. The little iterations. You try, you fail. You try again, you fail again. But you fail less every time. And we do it with math. And if a term like stochastic gradient descent intimidates you, trust me, it's actually not that hard. I am going to have to explain calculus to you. It's going to be entry-level calculus, but there will be calculus. But if you're only trying to understand just for fun and you're not trying to actually do the math, don't worry. You can ignore the math and just listen to the explanation. But those of you who are interested in this and wanting to get into it more, go get your calculus textbook back out and start brushing up on derivatives. And while you're doing that, I'll be seeing you.